This is a second example from today on a 3D rigid body equilibrium problem. And this one is fairly involved, so it might take us a little while to get through. What we have here is some kind of a sign. It says it's a 50-pound sign, and they tell us where the center of gravity of the sign is. It's right there at G in the middle of the sign. And of course, to make the math extra hard, the sign is off-centered here. So G does not, notice this is 2 feet and 3 feet, whereas G is 2.5 feet over. It's supported by a cable BC and a cable DE. And then at A, we are told that it is a smooth collar and it looks like it's round as well. So reminding you that at a smooth collar, we have two directions where it's completely free to move. So at A, it's going to be free to slide along that axis, which in this case happens to be the z-axis. So free to slide along the z-axis. So that means there will be no AZ, no reaction force at A in the z direction. And it'll also be free to rotate about that same axis. So there will be no moment at A about the z-axis. But it will prevent all the other motions. This is going to prevent us from moving in the x direction, prevent motion in the y, so we'll have an AX and an AY. It will also prevent this from spinning about the y-axis as well as from spinning about the x-axis because of the size of the collar. You can think of this as being basically a journal bearing, but since there's only one, we do want to include the reaction moments. We are going to start with a free body diagram, of course, and I'm going to draw my sign here, and it's being held by a collar back there at point A. And I removed two cables to draw this free body diagram. So I will have a tension in cable BC that I need to draw on here and a tension in cable DE because both of those cables are helping to hold up the sign. And then at A, I know there won't be a force at A in the Z direction, but there will be a force at A in the Y direction that I need to solve for, as well as a force at A in the X direction that I'll need to solve for. And I will also need to solve for two moments. One moment, MAY, I'll draw it that way, which means I'm assuming my right thumb points toward the positive Y direction, so we're rotating that way. And we will also have an MAX, which I'm also assuming a positive rotation, so thumb pointing toward the positive x-axis. Those are all of the supports. I had a tension in cable BC, tension in cable DE, and all of the four reactions at the smooth collar at A, but I also need to remember to put on here the weight of my sign, which was 50 pounds. And I believe that's everything that needs to go on my free body diagram. If I count up my unknowns, I get that I've got two tensions, TDE, TBC, AX, AY, and then two moments, MAX and MAY. So I've got a total of 6 unknowns to solve for. Good thing I can write 6 equations. Before we jump into writing the equations, this is a problem where I have a couple of cable tensions which are not pointed in the X, Y, and Z directions. So I want to write those using vectors. So let's write those first, get our vectors that we're going to need. Tension in cable BC as a vector. It has an unknown magnitude, which will plop out front. And then to get from B to C, in the X direction, B is currently 2 feet behind the YZ plane, and C is 3 feet behind the YZ plane. So I've got to go minus 1 foot in the X direction. In the Y direction, to get from B to C, I've got to go backwards, so a negative 2 feet. And then finally in the Z direction, this point looks to me like it's right down there in the XY plane. And so I've got to go up 2 feet to get to point C. And now I need to divide by the length of that position vector. So if I square 1 squared plus 2 squared plus 2 squared, I get exactly 9, square root it, and it's 3. So that rope happens to be exactly 3 feet long. And let's look at vector DE as well. It's got an unknown magnitude, and then the direction for DE, in the X direction, D is 3 feet away from the YZ plane, and E is 4 feet out. So I got to go plus 1 in the I direction. J direction, D is out here on the sign, E is back on the wall, so I'm going back a negative 2 feet. So minus 2j. And then finally, again, I'm down here. D is down here in the xy plane. So I got to go up to point E, and E is also 2 feet up. So we'll end up plus 2k and divide it by the total length, which again will be 3 feet long. So I've got all of my vectors now written down in their Cartesian components, so we can start doing equilibrium equations. Start by summing forces in the x. X direction is that way. And I'm going to have components from both of my cables. The x component is going to be minus 1/3 and plus 1/3. So I'll end up with minus 1/3 TBC plus 1/3 TDE. And what else is in the x direction on my free body diagram? The only other thing is this unknown AX. Plus AX equals 0. Great equation, but 3 unknowns, so save it for later, right? Maybe label it equation number 1. And let's write some more equations. Summation of forces in the y is going to be 0. I'll have the components from my tensions. One is minus 2/3. Oh, they're both minus 2/3. So I'll have minus 2/3 TBC, minus 2/3 TDE, and finally plus AY equals 0. There's a second equation. And let's do the z-force equation. Upward is positive. I'll have the two components of the tensions, so plus 2/3 TBC plus 2/3 TDE. And there is no reaction force at A in the z direction because that's a smooth collar, but I do have downward a 50-pound force. Minus 50 pounds equals 0. There is my third equation. In those 3 equations, I have 4 unknowns, so I'm not going to try to solve yet. I want to get some more equations before I try solving for anything. So up next, we're going to need to sum moments about 3 axes. And I think this is another case where it makes the most sense to just use the axes that are given in the drawing, because they all go through point A, and I have a lot of stuff going on at point A, so it's probably a good place to sum moments. Another place that might be good to sum moments would be this axis right here across the top of the sine, because you'd have your 2 tensions go right through that axis and would not cause a moment, and the 50 pounds also goes through that axis and would not cause a moment. So that might help us solve for something quickly as well. When I solve the problem, I just sum moments about the 3 axes through point A. So let's write those down. If I'm summing moments about the x-axis through point A, has to be 0, need a sign convention. And we do have a reaction moment about that axis, so make sure we include MAX in there. And now I need to figure out which of these forces on this diagram will cause a moment about the x-axis. So the x-axis is right here. That means AX and AY will not cause a moment because they go right through that axis. Actually, AX wouldn't anyway because it's parallel to the x-axis. And I don't need to include MAY, that's a moment about a totally different axis. But the 50-pound force very likely will cause a moment about that axis, as will possibly some component from these tensions. Start with a 50-pound force. It's straight down, 50 pounds. I just need a perpendicular distance from the axis, and it looks like it's just 2 feet out. So I'm going to have a 50 pounds times 2 feet away, and that, let's see if it's positive or negative. The axis is here. You got to come out this direction and then go down, so you're rotating that way. And if you curl your fingers that way, your thumb points in the negative x direction. So this needs to be a minus. And now let's look at those cable tensions. Remember, even though the cable tensions are complicated, they have components in all 3 directions, usually not all of them cause moments. For example, the x component is parallel to the x-axis and cannot possibly cause a moment about the x-axis. Only y and z forces can cause moments about the x-axis because they're perpendicular to it. So we don't need to worry about the x component of either of those tensions for this moment. We do maybe need to worry about, though, the y component and the z component. But wait a minute, did you see where that y component goes? It's directed directly through the x-axis. No distance away will not cause a moment. So the only component of the force in DE that's going to cause a moment about the x-axis is the vertical component, and the distance away is 2 feet. Same thing for BC. Distance away is 2 feet. So I need the z component of both of those cable tensions. TBC times 2/3. There's the z component, and the distance away is 2 feet. And I will also need TDE. 2/3 gives me the z component, and it's 2 feet away. It's all going to have to equal 0 when we're done. Now let's figure out if those are positive or negative moments. Think of it as right here, come out that direction. From the axis, come out that direction. Then you go up. You're rotating this way, which causes your thumb to go in the positive x direction. So it's going to be positive. Same here. Start at the x-axis, come out to the force. The force is going upward, so it's also going to be positive. So these two are going to be positive. So we got another equation, which is great. Unfortunately, it added another unknown. So I'm just going to call this equation 4 and set it aside for a minute. I want to point out to you guys what I did here. These pieces right here, these were both z forces. And what I multiplied them by were y distances, because I'm finding a moment about the x-axis. So you will always be multiplying z forces by y distances or y force components by z distances if you're doing moments about the x-axis. I could even include in here my 50-pound force. It is also a z force, also times a y distance. Let's do moments about another axis. What I did next in my notes is moment about the y-axis through point A. Where in the world is the y-axis? The y-axis is right through here, so at least the forces at A won't cause any moment. We will need to include MAY. So my y-axis is right here, and my weight is not directly under the y-axis. It's got a little perpendicular distance. So let's see if we can figure out where that is. It looks like it's going to be a 1/2 foot over, because can you see how this y-axis is 2 feet from the edge of the sign, but the center of gravity is 2.5 feet. So the difference is a little 1/2 foot distance. So I'm going to have 50 pounds times 0.5 feet away. Let's see if that's going to be positive or negative. My axis is here. If we go left and then down, that's going to cause a rotation this way about the axis. So my thumb, right thumb, will be pointing along the positive y-axis. So we're going to call this a positive moment. And now let's look at what we need to do with those tensions in the cables. Reminding you, the cable tensions are just made up of a z force, a y force, and an x force. So the y force will not cause a moment about the y-axis because it's parallel to the y-axis. The z force probably will, because it's pointed straight up there and it's got a distance away, or this one's pointed straight up there and it's got a distance away. So the z component will cause a moment. What about the x? Can you see how the x component is directed right to and through the y-axis in both cases? So the x component will not cause a moment. The only thing that will cause a moment about the y-axis, again, are the z components. So what I want to include in here are TBC times 2/3 is a z force again, and TDE times 2/3. It's all going to equal 0 when we're done. We need to multiply those by some distances. The vertical component of TBC has a perpendicular distance from the y-axis of 2 feet. So BC needs to be multiplied by 2 feet. And DE has a perpendicular distance from the y-axis of 3 feet. So we'll multiply that one by 3 feet. And now, are they positive or negative? BC, you start at the y-axis, go in that direction and then up. That is going to cause a positive moment about the y-axis. So the BC one is going to be positive. And what about the DE? We got to go left and then up. It's going to rotate that way. That one will be negative. So we put in a negative for that one. And we just wrote down another great equation and added yet another unknown. I'm just reminding you, though, in this case, all of the forces, once again, were z forces. But this time they're being multiplied not by y distances, but by x distances. Did you see how all those distances were in the x direction? This force times a little x distance. This vertical force times an x distance. And this vertical force times an x distance. So these distances were all x distances. That's the pattern you always have with moments. Let's get our last equation written. Summation of moments about the z-axis through point A is 0, and I'm calling the right-hand rule positive. So if my thumb points in the positive z direction, it's a positive moment. Okay, let's look at that z-axis. So this time there is no reaction moment. There was no MAZ, remember, because it's a smooth collar. And the weight will not cause a moment about the z-axis because it is in the z direction and it's parallel. So we just need to look at what these cable tensions are going to do. By the same argument that the weight won't cause a moment about the z-axis, the vertical components of these cable tensions will not cause a moment about the z-axis. But it's possible, in this case, that both the x components and the y components will, because none of them are pointed right at there. So we got to find the distances. So I'm going to end up needing to use, in this case, both the x and the y components of the cable tensions and multiply them by the appropriate distances away from the z-axis. So let me get those all written down. I'm going to end up needing, let's start with the cable BC maybe. I'll need a 2/3 TBC, and then I'll also need a 1/3 TBC. The 2/3 TBC will be the y component, and the 1/3 will be the x component, and we'll do the same thing with TDE. We're going to need a 2/3 TDE and a 1/3 TDE. Now I need to multiply all those by the right length. Okay, what is 2/3 TBC? That is the y component of TBC. That is pointed in the y direction right here. So I need a perpendicular distance from that y force to the z-axis. So you could think of it as this distance right here, which on the drawing is 2 feet. It's actually an x distance. So this gets multiplied by 2 feet, and at x, force is going back that direction. So you start at the axis, come out toward B, and go back in that direction. That is going to cause a positive moment about the z-axis. Let's do the other component of TBC. This one is going to be the x component. The x component is heading in that direction there because BC is going off in that way, and the x component is in the negative x direction. And we need a perpendicular distance. So the line of action of the force is here. Perpendicular distance is going to be 2 feet. And since you have to come out this way and go in that direction, that is going to cause also a positive moment about the z-axis. So you'll end up with plus, and it's also times 2 feet. Now let's look at TDE. The 2/3 piece is the y component, so that's going this way. And we need a perpendicular distance between it and the z-axis. That's going to be our 3 feet. So multiply that times 3 feet, and that's our y force times an x distance. So we're coming from the axis out 3 feet in the x, and then we're going in that direction. That is going to cause, with the right-hand rule, a negative moment about the z-axis. So put in a negative. And finally, 1/3 TDE. That's the x component of this force, which is pointed that way. So from the z-axis, I need to come out here. It's a 2-foot distance. And if you come out that way and go there, we're going to be rotating that way, which is also a negative moment. So the distance was 2 feet, and it was negative. So just reminding you, this one is the most complicated of all the moments. We have a combination of x forces and y distances and y forces and x distances. So let's group those together. We've got y forces. There's a y force, and there's a y force. So these two are both y forces. They both get multiplied by x distances. We also had some x forces here. The 1/3 of each of these guys were x forces, and they both get multiplied by y distances. This is equation number 6. We have 6 equations we should be able to solve. My approach is, I like this equation that we just barely wrote because it's only got TBC and TDE in it. Simplify equation 6, and if we simplify equation 6, TBC is equal to 4/3 of TDE. Now let's see if we can find another equation that only has those 2 cable tensions in it. Look at equation number 3. If I put that into equation number 3, I should be able to solve for those cable tensions. We substitute into equation 3. Doing that, I'll end up with what? Equation 3 said 2/3 TBC, which is 4/3 TDE, plus 2/3 TDE, minus 50 pounds equals 0. We solve that, we end up getting that TDE is equal to 32.1 pounds. Then we substitute it back in up above, multiply that by 4/3, and we get that TBC comes out to be 42.9 pounds. Now, this is a back substitute into all of our other equations. If you notice, all of these other equations, they each only had one more unknown. This one has AX in it, this one has AY in it, this has MAX, and this one has MAY. So if we plug in those tensions in all these other equations, we'll get all of the other things. So solving the rest, we end up getting that AX is 3.57 pounds, AY comes out to be 50 pounds, MAX comes out to be 0, and MAY comes out to be minus 17.9 pound-feet or feet-pounds. These three moment equations are really, really hard to do if you are new at this. If you're really struggling to find those distances and to figure out if they're positive or negative, I want to show you a different way that I want you to do it, and it's using vector cross products. So here is the cross product way to solve the exact same problem. All we need to do is get those moment equations. So what we're doing with the cross product is we want to sum all of the vector moments about a point like point A and make it equal to 0. If you wanted to sum moments about axes that didn't all go through the same point, you could do that as well. But if you do them all about the same point, this is actually, you can kind of do it fairly efficiently. So what I'm going to do is I'm going to write this as I first of all got my unknown reaction moments. Well, I've got MAX. Oh, that's actually a moment about the x-axis, so call it an I component. I've also got MAY that is unknown, and that's a moment about the j-axis. Now I also need to add in here the moments that all of the other force vectors cause about point A. So to do that, you put ijk across the top of your cross product. Then the next row is the position vector. So this is a vector that takes you from point A to the force vector. Why don't we do the weight first? The weight is 0, 0, minus 50 pounds. So I need a position vector that takes me from point A to G, right there, from A to G. So to get from A to G, I needed to go a half a foot in the x direction. I needed to go 2 feet in the y direction, and it looks like I need to go down 1 foot in the z direction. So let's put all of those numbers into our cross product. We need to go 0.5 feet in the x direction, 2 feet in the y direction, and minus 1 foot in the z direction. And that will give me that very first moment, the moment that gets caused by the 50-pound force. Then we need to add 2 more of these. ijk on the top, and then our force vectors go on the bottom. So one of them we could do minus 1/3 TBC, minus 2/3 TBC, and then plus 2/3 TBC. The other one becomes plus 1/3 TDE. It was minus 2/3 TDE, and then finally plus 2/3 TDE. Now I need a position vector to get me from A to this cable and from A to this other cable. And you can do this however you like. You can either go from A out to D or from A up to E. It will work either way. So if I want to go from A to D, for example, I would come out 2 feet in the y direction and 3 feet in the x direction. I don't have to go up or down at all. So for DE, I needed to go 3 feet in the x and 2 feet in the y and 0 in the k. And to get to cable BC from point A, I go 2 feet in the y and minus 2 feet in the x. So I put in here minus 2 feet in the x plus 2 feet in the y and 0 in the k. That is actually those 3 moment equations written down cross product style. So our task at this point now is to actually evaluate all of those cross products. My favorite way to do that is that basket weave technique that I've shown you before. Take your cross product, copy, paste, and then you want to take your first 2 columns, copy and paste, And then we're going to go 2 different directions here. Pick whatever colors you want. Going this direction, we're going to add, add, add. So that's going to be I times 2 feet times minus 50 pounds plus 0J plus 0K. And then the other direction, we're going to subtract, minus, minus, minus. So you end up getting minus 0K minus 0I minus, there'll be a J times 0.5 feet times minus 50 pounds. Be very, very careful of your signs here, both the signs inside the cross product as well as whether you're doing the positive or the negative direction. One sign mistake and it will all go badly. Let's do the next one. Take the next one over, and then we're going to take the first 2 columns and same process, use the same colors even. Plus, plus, plus. I'll end up with I times 2 feet times 2/3 TBC plus J times 0 plus K times minus 2 feet times minus 2/3 TBC. And then minus, 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 other way. Minus, minus, minus. So we'll do minus K times 2 feet times minus 1/3 TBC minus 0I, and finally minus J times minus 2 feet times 2/3 TBC. And let's do the last one. And same story, pluses this way. We end up getting I times 2 feet times 2/3 TDE plus 0J plus K times 3 feet times minus 2/3 TDE. And then the minus ones, minus K times 2 feet times 1/3 TDE minus 0I minus J times 3 feet times 2/3 TDE. We're going to add all these up, but in order for the moment vector to be 0, we need the x component to be 0, the y component to be 0, and the z component to be 0. So what I want to do is combining I, j, and k terms in 3 equations. So if I do all of the I terms, so combining the I terms, here's what it's going to look like. All the way back to the beginning, I have an MAX, and I have a 2 feet times minus 50 pounds, and there's an I, that one's 0, there's an I, and that's it. So combining all of the I terms, I end up with MAX plus the 2 feet times minus 50 pounds, plus I end up with 2 feet times 2/3 TBC, plus 2 feet times 2/3 TDE, and it has to be 0. That should be exactly the same as equation number 4 up above when I sum moments. So look exactly the same. MAX minus 50 pounds times 2 feet, and I've got the 2/3 of each of the cables, both times 2 feet. Same exact equation. That's really encouraging. And then if I combine J terms, I end up with an MAY, the reaction moment that I want to solve for, and then I need all the J's. See what other J's I have. This term will give me a J times half a foot times 50, and I've got a minus and a minus, which will become a positive. I've got that one's a 0. There's a J term, 2 feet and 2/3 TBC. And here is another J term, 3 feet and 2/3 TDE. So let's write those all down. MAY minus 0.5 feet times minus 50 pounds, minus, I've got minus 2 feet times 2/3 TBC, and finally minus 3 feet times 2/3 TDE equals 0. Should match equation 5. So should we see if it matches? Equation 5 ended up being plus 50 pounds times a half foot. The TBC ended up being plus 2/3 of it times 2 feet, and TDE was minus 2/3 times 3 feet. Those numbers are looking familiar. I got the half times 50, and when you cancel out those minuses, you do get plus. The TBC comes out to be plus also, like it should, and it's got a 2 feet times the 2/3, and the TDE stays negative, and it's got a 3 feet times the 2/3. It matches exactly. Finally, combining K terms. I don't have a reaction moment in the Z direction, so it's only going to be from these cross products, and the first one, I get 0 and 0. Second one, I get these two pieces with TBC in them, and then I get these two pieces with TDE in them. So writing those all down, I end up getting minus 2 feet times minus 2/3 TBC minus positive 2 feet times minus 1/3 TBC plus 3 feet times minus 2/3 TDE minus 2 feet times 1/3 TDE equals 0. And that should match equation 6. You'll remember equation 6 only had cable tensions in it, no weight, no reaction moments, no reaction forces, and we had a combination of 2 feet and 3 feet in it. The term that had the 3 feet was the 2/3 TDE, and it had a negative. The other term with DE also had a negative. So let's see if that matches what we've got. The term with 3 feet had a 2/3 and a negative, and the other term with DE also had a negative. And can you see both of the TBC terms both end up being positive? So I think it matches. And that is the alternative way to solve this. I think it's a little bit slower, and you do have to be super meticulous with your signs. So that's the downside to it. The upside is you don't have to be very good at visualizing perpendicular distances, figuring out which component does or doesn't cause a moment. So I tend to only use this method when I have a problem like this where it's a pretty complicated force vector and the position vector is also fairly complicated. It takes a while, but if you're careful and methodical, you can get through and get to the right answer.